Hello, everybody, and welcome back to my basement. I am here today to record a lecture to describe example 5b. So, this is within the context of examining unique effects in general linear models. So, we're going to be first evaluating a series of bivariate relationships between one predictor and our quantitative outcome. And then at the end of this example, we will put all of the predictors into the same model to be able to examine their unique effects. So I had built this handout to illustrate not only the unique effects at the end, but to serve as a review of all of the things that we've talked about up to this point. So most of this is going to be familiar territory. We are looking at a new data set as an example. This is the data set that's featured in my book, the Longitudinal Analysis book, Chapter 2. The example 5b here does not follow Chapter 2 exactly. Chapter 2 did a hierarchical analysis, but does use the same data. So these are fake data as usual. We have 550 older adults. We are going to be predicting a measure of cognitive functioning. So we'll call that cognition, which is measured by an information test. It's a measure of crystallized intelligence. And the predictors that we're going to be looking at are chronological age in years, grip strength in pounds per square inch as a measure of physical function. That's a common way of controlling for physical functioning differences in older adults. We'll also be examining gender, with men as the reference, and a predictor for dementia diagnosis status. So the story behind these data is that they are the baseline observation of a longitudinal study with older adults in which one of three things could happen. Each participant could never be diagnosed with dementia during the study or afterwards. They could be diagnosed with dementia at some point after baseline, but not yet, not at this occasion. Or they could already have been diagnosed with dementia at this occasion. So there's three possibilities. We'll be treating that as a categorical predictor. In terms of importing the data, I'm following the code that I used for Chapter 2, in which I'm importing a data set in the native program for each of Stata and SAS. So starting with SAS, the code looks a little bit different because I'm going to be importing a SAS data set, not an Excel sheet. Has some similar features. So we start by putting the path location to where these files are going to be located. And this line is new. This line right here is what's known as a library statement. In SAS, libraries refer to places. You can have as many places as you want to, and this is a place in particular that stores SAS datasets. So it's an internal SAS mechanism. And what I am doing is creating a place that shares the same name file save that this path refers to, and I am defining the place with an abbreviation. So we're using the same technology that we've used in terms of not having to type the path out each time we refer to it in the code. When we see this combination of ampersand, the name, followed by a period, that is invoking whatever we've defined file save to be up to this point. So it's like a find and replace mechanism. So every time I type this file save, it's going to refer up to whatever I've defined it as up here. I don't have to retype it each time. So this is a long way of saying I am defining an internal SAS location that has the same address as this folder that has all of my materials. I am then going to be able to import SAS datasets directly from this file save place. And that happens in this line right here. So the way that you can understand this data set combination is data means make me a new data set. So I am creating a new data set in the work temporary library. It is going to be called example 5b. Set means from. So what I am doing is importing from this file save permanent library the data set that is named SAS underscore chapter 2, which is from the materials for the book. So essentially what I'm doing is importing the data set from this permanent location, saving a copy of it in a different location, the temporary directory. That way my SAS data set stays safe and sound in the permanent place, and the one that I'm working with is in the temporary directory. That way, in case I screw up, I don't harm the original data. So work.example_b is the name of the dataset copy that I'm going to be modifying with the following code. In this example, I am doing all of the data transformations that I need to be able to create my predictor variables in one step. So in life, I tend to do things this way. It's more efficient. It makes it easier to avoid having different snippets of code that you have to run in sections if it's all in one place. So I am going to first center my quantitative predictors, and I have chosen values that are near their means. So age is going to be centered at 85, and grip strength is going to be centered at 9, which translates into 9 pounds per square inch in this measure. My convention in labeling new variables and naming them is to put the centering constant at the end. So age 85 to me means age centered at 85. Grip 9 means grip strength centered at 9. So the new name goes before the equal sign. The old column that information is coming from goes after the equal sign, and then we subtract the constant that we want to become the new 0 point for this variable. And of course, each transformation ends in the very important semicolon that the SAS language relies on quite heavily. Next up is the process of creating contrast variables or reference dummy codes to distinguish between the three types of dementia groups. So the DEM group is the original variable that's coded 1, 2, or 3, where 1 means none, 2 means future, and 3 means current. So that's what the comments out here to the right are reminding me. I am going to set it up so that the none group, which is group 1, is my reference. That's the group that's the largest in the data set, and it makes sense as a reference point. So I am going to have dem nf as one of my variables, which is going to stand for none versus future, and dem nc, which is going to stand for none versus current. So if group equals 1, I'm going to create two new variables. Actually, I'm going to replace values for the two new variables I've already created. So I've created new variables in this step. They're empty. I'm then going to fill them with zeros or ones based on whether or not we're talking about group 1, 2, or 3. So group 1, both variables I'm creating here, I'm recoding, excuse me, are going to have zeros. That denotes the none group, dem group equals 1 as my reference. If group equals 2, the first dummy code variable is going to turn on, so it's going to distinguish none versus future. And if we're talking about group 3, the second variable turns on to distinguish none versus current. That means the remaining group contrast of future versus current is going to have to be found as a linear combination of the slopes of these two new predictors. So creating all in all 4 new predictors to be able to use in these models. I'm also going to have gender, which is already coded such that 0 is men and 1 is women, so I can enter that predictor directly. And cognition is going to be the outcome. I am including a function here, the nmiss function, so that I can select only participants who have complete information on all of the variables I'm going to examine. I'm doing that so that the sample size stays constant across my analyses. No matter which variables happen to be included in a given model, it's going to be using the same sample. There's no missing data in this particular data set, but I include this here because that's something that you'll want to think about ahead of time when you are running these sorts of models in life. So that's data import and creating predictor variables using SAS. Here are the same steps using Stata. So I'm defining file save to be the same folder location. I am importing a Stata format of the data file, so that's the .dta extension. So rather than import, the command is just use. And note that the reference for file save, the way that it works in Stata, is the $ and then the name. So that is filling in this entire path every time we have file save with the $sign printed here. And then clear means that if the data set already is in memory, then I'm allowed to reopen it and write over it, which is handy if I happen to make a mistake and I need to re-import the data. I will note that when I created this data set, I exported it actually out of SAS, and what SAS does by default is convert all variable names to lowercase, since that is Stata's preference. So case matters in Stata variable names, it's case sensitive, and so that's why we have NF in lowercase, for instance, and NC in lowercase, because that's what they were, that is consistent with the rest of how the variables are named. So just like we did in SAS, I'm going to start by creating centered versions of my predictors. So the command gen, which stands for generate, is used to create a new variable, age 85, as a function of the old variable age minus 85, and grip 9 pounds per square inch from the old variable called grip. I am generating 2 dummy-coded contrasts to distinguish my 3 dementia groups. None is going to be my reference, and so NF to me means none versus future, group 1 versus 2, and NC means none versus current, which is group 1 versus 3. And so then the code down here systematically replaces these 2 empty variables with zeros or ones based on them meeting the condition of which dem group is which. And note that when you assign zeros or ones, it's a single equals, whereas if you are asking it to evaluate whether a variable is equal to a particular value, an evaluation rather than an assignment, that's 2 equal signs. So if dem group equal 1, then we want each of my new variables to take on 0 values. If dem group is 2, the first variable takes on a 1 instead, and if dem group is 3, the second variable takes on a 1 instead. We then label all of the variables, and the same process of selecting cases that are complete with respect to all the variables we will eventually need is done with an egen. So I think of egen as a fancier version of gen. And I'm creating a new variable that holds the number missing. So row miss is the function that counts up the number of missing. And then I'm instructing Stata to drop those cases that have nmiss greater than 0 or any missing data. Next step is to examine the distributions of the variables that I'm going to be working with. And this is where I got the constants by which I would do the centering. So in SAS, it's proc means to examine means, standard deviations, and ranges for quantitative variables. No labels just suppresses the labels on the variables. It makes the table a little bit easier to fit onto the page. And ndes equals 3 controls the number of digits printed after the decimal. By default, you get mean, standard deviation, min, and max. You don't get variance, which I have added here with the keyword var, and I'm telling it which data set to use. Var here is a list of which variables you want the means for. So even though it's the same word twice, they mean different things. In the proc means line, this refers to variance, whereas var here refers to the list of variables for which you want summary information. The same command in Stata is summarize. I'm using a format statement before that to control the printing of decimals to make it look the same as what it would be in SAS, although that's not strictly necessary. I just wanted the output to be nicely formatted. So the detail command, so I have this twice because detail would also add variance, and so it creates additional output, variance percentiles, medians, and so forth. So here are the descriptive statistics for my variables of interest. Cognition is going to be my outcome, and I note that it has a mean of about 25 and it has a variance of 120. So this variance of 120 is what the empty model predicting cognition is going to be recreating, and the empty model predicting cognition will have the mean as the intercept. So if you don't know anything else about a person, your best guess for their outcome is the mean, and so the empty model is going to be recreating those 2 values right here, the mean as the fixed intercept and the variance as the residual variance. Age has a mean near 85, so I picked 85 as a centering constant. Grip strength has a mean near 9, so that's what I picked. And even though it seems a little odd to compute a mean for a binary variable, what this means is that 58% of the cases have a value of 1, which in this context means women. So 58% women, and the remainder are men. I also asked for a cross tabulation of my two categorical predictors, so a repeat here of sex, as well as the three group dementia group. So we can look at the combinations of these. These two variables will eventually have an interaction in the model, and so this table is foreshadowing the power that we have to detect differences across each of these various cells. So most of the people are in the dementia equals 1, no dementia group, with fewer people who will eventually be diagnosed, the 2 group, or who have already currently been diagnosed, the 3 group. I also asked for pictures just to get a sense of the overall distributions of these variables. So age, grip strength, and cognition, the quantitative variables I'm working with. And it looks like age has a little bit of positive skew to it. Grip strength is relatively normally distributed, and cognition is relatively normally distributed as well. Maybe a little wonky over here, but that's okay. By the way, foreshadowing what we're eventually going to end up with, this is what the distribution of the residuals will look like for cognition after we're done adding in all of our model predictors. That's what is supposed to be normal in order to use the general linear model and have faith in the results of the standard errors and p-values that is provided. So next step. So we've done univariate variable description. Now we're doing bivariate. And so for the variables that we can express their bivariate relationships using Pearson's correlation, I have asked for that information. So that includes the cognition outcome, the age and grip quantitative predictors, the sex binary predictor, but it does not include dementia group. I can't have a correlation with a 3-group variable expressed as one single correlation value. So I have a note here that we're not going to be looking at that because the meaning of the dementia group contrasts doesn't hold when they're considered in isolation. They have to be considered together for them to actually represent the group differences that they were created to produce. So we're not going to look at dementia as part of our bivariate analysis here. So it's proc core in SAS. No simple, by the way, just suppresses additional output related to the means, variances, and such that we've already seen. I am also saving the correlations between these variables to a data set. That's handy to be able to strip out the p-values and sample sizes if you need to create a correlation matrix for reporting purposes, which I have at the end of this example. In Stata, I'm using the command pwcore, stands for pairwise correlation, and I've asked it to give me p-values for those correlations as well. So here's some SAS output. So the values on the first line for each of these cells are the Pearson correlation estimates, and the values underneath are the p-values that correspond to the t-test statistic it is computing for you behind the scenes. So just to remind you, Pearson's correlation is being tested against a null hypothesis of rho equals 0, meaning against a population correlation of 0 as our expectation. And the p-values give us the probability of observing each of these correlations, that correlation or more extreme, if the null hypothesis of no correlation were true. So how unlikely is it that we would see these numbers if there was no correlation in the population? That's what the p-values are trying to convey. The information on the top, so above the diagonal, so to speak, is exactly the same as the information below. So we can look at one or the other. Below the diagonal is where we are here, so let's stick with that. So the correlation between age and cognition is minus 0.17. So that means as age goes up, cognition is predicted to go down. It's a relatively small effect, correlation of only 0.17, but we have 550 people. So that correlation is actually significantly different than 0. It would be unlikely to observe a correlation that large or larger if there were no correlation in the population. Another bivariate relationship we can look at is between cognition and grip strength. So this is a positive correlation of 0.24, which means as grip strength goes up, cognition is also predicted to go up, and that is a significant positive correlation. And last but not least, we have cognition with gender. So to interpret this correlation, you have to know how the variable is coded. In this case, men are the 0 and the women are the 1. So the negative correlation, the negative 0.24 that I have here means as gender goes up, meaning women, cognition goes down. So this correlation is saying that women are predicted to have significantly lower cognition than men. That being in the 1 group is associated with less cognition. Significantly so, given the p-value against an alpha of 0.05. We can also look at the correlations between the predictors as foreshadowing what's going to happen when we put multiple predictors into the same model. So for instance, age and grip strength are negatively correlated. As grip strength goes up, age goes down. As age goes up, grip strength goes down. So that means that their effects in the same model are likely to be smaller than their effects when each of them is examined in isolation. They have some covariance, they share some overlap. So the model will partition variability that they have in common, as indicated with this correlation between them, from variability that they each have independently, and to see the extent to which each of those is related to cognition as our outcome. Age and gender are not correlated in this sample, so women and men are not expected to be different in age, is another way of thinking about it. The p-value is 0.29. So if there were truly no correlation between age and gender in the sample, we would observe a correlation of 0.05 or larger about 29% of the time. Last but not least, gender and grip strength. As gender goes up, grip strength goes down, which means women are predicted to have significantly lower grip strength. And this is the largest effect that we have on the page here. So we would expect that the effect of grip strength and gender in predicting cognition would differ because they share some common variance. They would differ when each predictor is included by itself versus when they're paired together and put in competition with each other. So all of these relationships are linear relationships. When we're talking about a binary predictor like gender, that's all you can have because there's only a 1 unit change possible between 0 and 1. But for the variables that are quantitative, cognition, age, and grip strength, it's possible that age and grip strength could have nonlinear relationships with cognition in addition to linear relationships. So we're going to estimate models to be able to examine that possibility. But this correlation matrix gives us a sense of sort of the broader picture of whether or not there's some kind of relationship in a linear form amongst these variables. Okay, so then we can dive into the process of modeling. So cognition is our outcome. So cognition for each individual, that's why we have an I subscript. We're going to start with an empty model in which there are no predictors. So each person's predicted cognition is just given by beta 0. In a model with no predictors, beta 0 is going to take on the mean of cognition. If you don't know anything else about a person, your best guess for their outcome is just the mean for that variable, because the mean is supposed to be the most likely. E sub I is the residual for each person, how far off their actual cognition value is from the mean. So the variability across these E's, across people, that is the variance in cognition. So another way of thinking about the empty model is that it is the definition of how we compute variance. It's each case minus the mean squared, summed over cases, divided by sample size, minus 1. So in life, I would generally not bother to fit an empty model. an empty general linear model, but this is useful for pedagogical purposes to remind us how the R-square values get computed, because this is the baseline that we use for computing them. So SAS, in this case, gives us our residual variance. So 120 is the variability in cognition. And so that was exactly the same thing that we saw in just looking at the descriptive statistics for cognition, because this is all of the variability that there is to be had. From here, our job is to enter predictors into the model that hopefully account for some of this variability and thus bring this residual variance down. Another way of saying that this is all of the variability that there is to be had in cognition is that the R-square is exactly 0. We haven't explained any of it yet because we haven't put any explainers in the model. So cognition is the outcome. The comma in stata delineates options. There's no predictors in the model. The intercept is the sample mean. So this is our jumping off point. From here, our job is to customize the predicted cognition outcome for each person by adding in predictive information. So let's try age. We can start with a model examining a linear effective age. I am writing the equation to describe the centering of age. So anyone looking at this equation should know that age 0 refers to an 85-year-old under this centering scheme. So the model now has two fixed effects, a beta 0 fixed intercept and a beta 1 fixed slope for the linear effective age. So age goes into the model as a predictor here, and c dot age 85 as a predictor here in stata. I am also saving pieces of the output, by the way, to compute effect sizes, but that's not something you would typically need to do for every model. I'm just demonstrating how to do it here. So our results then, we have the overall test of the model given by the first two boxes of the SAS output. So we only have one slope in the model, the effective age. We do have a significant model, meaning that there is a significant relationship between cognition as predicted by age and the real cognition. That conclusion is the same thing that we would get in just looking at the slope for age by itself. So this line that I've highlighted at the bottom, the solution for the age slope, is telling you the exact same information as the F value for the model, and that's because there is only one effective age in the model. So the slope is the model at this point. If I took this t value of -4 and squared it, I would get this F of 16. We have an R-square of about 0.03. So 3% of the variability in cognition has been explained by a linear effective age, bringing the cognition variance down from its original value of 120 down to 117. I've included some extra output that I don't typically show just to make the point that the slope is the same thing as the model. So there's a table here that breaks down the sums of squares for every term in the model. 1926 is the sums of squares that is attributable to age, and that's exactly the same thing as what the sums of squares for the model is, because the one age slope is the model at this point. Likewise, semi-partial eta square, which is computed as the sums of squares for the slope over the total sums of squares. So total sums of squares is given right here. Sums of squares for the slope is given right here. That gives you the amount of variability that is due to that particular predictor. Given that that predictor is the only thing in the model at this point, the semi-partial eta square for its effect size is exactly the same as the R-square for the model. So the model is the slope. In terms of interpreting our results, our intercept is now specifically the cognition score that is predicted for someone who's 85. So an 85-year-old is predicted to have a score of about 24. And for every year older, that score is expected to go down, it's a negative slope, by 0.5. So people who are older are expected to have lower levels of cognition. They are expected to have a half a point lower per year older. And this slope is statistically significant. Just to remind you, if I take this slope estimate of negative 0.54, divide it by its standard error of 0.13, that ratio creates this t of -4, and relative to a critical distribution based on our sample size of 550 and having only one slope in the model, which creates degrees of freedom of 548, the t-value is significant. So it is unlikely that we would see a slope this big if the true slope in the population were 0. And just to remind you what standard errors mean, the standard error of the intercept is how far off on average a sample intercept is expected to be from the population intercept. The standard error for the slope is how far off on average the sample slope is expected to be from the population slope. So these numbers are trying to address the expected inconsistency of these estimates if you were to redo the study using the same sample size repeatedly. They're trying to approximate the standard deviation of the sampling distribution of each of these parameters. I have also taken this table, saved it as a SAS dataset, and used it inside the dataset, computed a Cohen's d measure of effect size, as well as an R measure of effect size. And I'm doing that here largely for pedagogical purposes, because what ends up happening, here's the results of those two transformations, which I've appended to my output. The R that I get from converting the t-value in degrees of freedom is exactly the same thing as the Pearson's R that I got above. And if I were to take this R and square it, I would get the R square for the model, which is just this slope. So this model is simply reproducing the Pearson correlation. The reason that I would do a model instead of just looking at a Pearson correlation is actually to expand it to be able to address nonlinear relationships. So that's what we're going to do next. So the linear model is a comparison model against which to judge whether or not adding a squared term significantly predicts cognition better than having only a linear term. So this allows the slope as a function of age to vary. It's known as acceleration or deceleration in physics terms. You can think of it as a bendy line. It allows the effective age to slow down or to speed up, depending on the signs of each of these slopes. So I'm adding a squared term in SAS by entering age star age. So it's an interaction term that's created on the fly. The same thing happens in Stata by using a hashtag between the two ages. I'm also asking for a semi-partial correlation out of the Stata output so that I can get that for each slope. So here's my model. Now I have 2 degrees of freedom for the model because I have 2 slopes, linear age and quadratic age. Because I have estimated 2 slopes, I have 547 degrees of freedom left over for a corrected total of 549. Given my sample size of 550, the one missing is for the intercept, which is always included. My variability has is variability in cognition. The residual variance is 117, which is pretty close to what it was before. Let me double check. 117.46 versus 117.61. So it actually went up a tiny bit. This illustrates why R square is computed using sums of squares rather than mean squares, because that way the R square can't become negative. You can't make a model worse by adding something to it. with that method of computation. But basically the R-square is about the same as what it was before, 029054 versus 029590. So just a tiny, tiny increment. The model is still significant, but note that the f-test for the significance of the model is 8 relative to the previous model, which was actually higher. It was 16. And that's because you can think of f as a per slope quantity. It's information captured per slope divided by information remaining per slope you could have added. So the fact that we have one slope that is not helping us, so looking at the output down here, the quadratic slope that we've added is basically 0. The fact that it's not helping us means the test of the model is being down-weighted by having one good slope and one bad slope. The average contribution looks worse because of the bad slope. So in terms of interpreting the results of this addition to the model, here's the semi-partial eta square for the new term. Adding quadratic age accounts for another 0.0005 of an R-square. The individual coefficient itself is not significantly different than 0, so this indicates that adding a squared term does not help us predict cognition any better than would just having linear effective age. If we were to interpret the direction of these effects, we would have to keep in mind that the intercept and the linear slope of age now are both conditional on age 85. More generally, anytime you have an interaction term, the effect of one of the predictors that's part of it is specific to the interacting predictor being 0. So in this case, the interacting predictor is itself, which means age 85's slope is conditional on when it's 0, which is 85. So what this means is that the intercept of the expected cognition outcome for an 85-year-old of 24 at age 85, the instantaneous age slope is minus 0.6. So you can picture this as the slope that would be tangent to the curve at that point. At age 85, for every year older you are, you lose 0.6 of a score in cognition. What the quadratic slope is doing to it, this combination is going to be a less negative. So the linear slope for age is negative. The quadratic slope for age is positive. So they're working against each other. So what's going to happen is that the slope of age, which is negative, is going to become less negative as age increases. So you're looking at sort of the left-hand side of a U here. However, it's not significantly negative. So functionally speaking, a linear slope appears to be sufficient. So that's what we'll do, is we'll just stick with that. And here are the effect sizes I computed using the t-test statistic to describe the linear and quadratic slopes. Same idea, now using grip strength. So this process that we're doing right now is looking at bivariate relationships. How does each potential predictor relate to the outcome all by itself? And trying to make sure that we've properly specified the effect of each predictor before considering what happens when they're combined into the same model as competitors. So we're going to look, we just finished looking at linear and quadratic effects of age, decided that linear was good enough. Now we're going to do the same thing using grip strength. So age is out of the model temporarily. Grip strength, which is pounds per square inch, has come in. We've centered it at 9, so grip 9 is the new reference point for the model. With one slope, the f-test for the model is the squared version of the t-test for the slope. So this is a situation in which if you only have one slope, the test of the slope is the test of the model. The semi-partial eta square for that one slope is the R-square for the model. So it looks like the grip strength slope that we've added is significant, which means that the R-square for the model is significant. So our residual variance that started out at 120 is down to about 114. That is a reduction of about 5.8%. So the intercept in this model is still around 24. That is the expected cognition score for someone with 9 pounds of grip strength per square inch. For every additional pound, your cognition outcome is expected to go up by 0.9. So stronger people are expected to do better on the information test, significantly so. It is unlikely to find a slope this big or larger if the true slope in the population were 0. And again, the effect size that I'm computing using the t-test statistic, so there's the formula that converts t into r. The r that results is exactly the same thing as a Pearson correlation. So this model that has only a linear effect of grip strength is functionally the same thing as a Pearson correlation. I'm going to expand the model by adding grip strength, a squared term for it, the same way we did for age. So adding it in SAS using a star, adding it into Stata using a hashtag. And the pattern of results is actually very similar to what happened for age. Even though the overall model is significant with the two slopes, if we look at their individual contributions, the linear effect of grip strength is responsible for the bulk of the R-square. A tiny bit is attributable to the quadratic effect of grip strength. And if we look at the solution, the quadratic slope is not significant. So it looks like we probably don't need it. But for completeness, we can talk about what each of these parameter estimates means. The intercept of 24 is the expected cognition outcome for someone with a grip strength of 9. Specifically at a grip strength of 9 is what this linear slope refers to, the instantaneous linear slope when the predictor equals 0, which is 9 pounds. At that point, for every unit higher grip you have, cognition is predicted to go up by 0.89. The combination of that positive linear grip slope paired with a positive quadratic grip slope creates a more positive situation where we have a positive slope that becomes more positive, so an acceleration. So we're looking at the right-hand side of a traditional U shape as what is predicted by this combination of coefficients. However, the grip strength quadratic slope, not significant, doesn't account for any variance, practically none, so therefore we probably don't need it in the model. Next step, gender. Binary predictor. It can only possibly have a linear slope because you can only move from a value of 0 to a value of 1, which means going from men as the reference group up to women as the alternative group. This is again going to give us the same information as a Pearson correlation. But I'm putting it in here to remind us how to interpret differences for each group. The model is going to directly give me the predicted cognition for men who are the 0 group. That's given by the fixed intercept. The predicted cognition for women is going to be a linear combination of the fixed intercept plus the slope for gender times 1, which is the value that gender takes for women. And the difference between them is given directly by the slope. So we have gender as a predictor in the model. I have written out these 3 predictions. Even though 2 of them are redundant with the solution, I wrote them all out for pedagogical reasons. Those 3 lines are echoed right here in SAS, and they're echoed right here in Stata. So any estimates or lincoms where you want to create a predicted outcome, every term in the model goes into that prediction, including the intercept. And the values after the predictors are the values of the predictor variables for which you want the prediction. So the first line refers to the prediction for men when this variable is coded 0. The second line refers to the predicted outcome for women when this variable is coded 1. And the difference between them is given directly by the slope. So that when you type out sex MW here, what you're actually referring to under the hood is the slope beta 1. So SAS is going to take the results of what beta 1 is and use that here to get you the requested quantities. This idea that what you're actually doing is multiplying the coefficient that you give and adding them together is made explicit in the way that Stata insists on these things, where we have constant with an underscore instead of intercept times 1 plus the gender slope times the value of gender for that particular individual. So we have a significant model. Again, this is a case where the model is the same thing as the slope. So if I took this f value for the model that has one slope in it, and I took the square root of f, that would give me the t for the slope down here. Likewise, the semi-partial eta square for the one slope is the same thing as the r square for the model. So there's a one-to-one correspondence. And if I were to compute an effect size for this gender difference in a correlation metric, that would be the same as the Pearson correlation. But we do get the actual estimate of the means for each group as well as their difference. So the first table here, this is the solution for fixed effects that you would get normally by default. So 27 is the predicted outcome when gender is coded 0, that's men, and -5 is going to be the slope for gender. So that is what happens when you go from a gender of 0 up to 1, when you go from men up to women. And because the slope is negative, what that means is that women as the one group are actually lower. They're lower by 5, significantly lower given the p-value. So if we take 27 as the estimate for what men are predicted to get, we subtract 5 from it to give us the gender difference. The result is about 22, which is what's given as the linear combination of those two numbers as given by the estimate statements or the LINCOM statements in Stata. Last but not least, we're examining the bivariate effect of dementia group, where we have both dummy-coded predictors included in the model at the same time. They have to both be in here in order for the interpretations that we've given them to hold. The way that we've computed these variables is such that when both of them are 0, we're talking about the none group as the reference. We're talking about the future group when dem nf is 1, and we're talking about the current group when dem nc is 1 instead. So that means the none group, their mean is given directly by the intercept because the slope terms 0 out. The future group, their mean is given by the intercept plus the effect of beta 1. And for the current group, their mean is given by the intercept plus the effect of beta 2. So these two parameters for the alternative group means have to be requested separately because they are linear combinations of the estimated fixed effects, whereas the none mean is given directly by just the intercept. Likewise, 2 of the 3 differences between these 3 groups, the differences that are relative to the none group as the reference, those are given directly by the beta 1 and beta 2 slopes. So none versus future, if we take how the model finds the mean for future, which is the term beta 0 plus beta 1, and subtract from it how the model finds the none mean, which is just beta 0, beta 0's drop, you're left with beta 1. Same idea for the current group. And last but not least, the group difference among the non-reference groups in this type of coding scheme is always going to have to be found as a linear combination. So we have how the model gets the mean for current minus how the model gets the mean for future, and that works out to be the difference between slopes. So current minus future gives us the difference between those two group means implied by the model. That extra linear combination is right here. So I have a contrast statement that is without commas. So what I'm doing is actually asking it to create a difference in two slopes as the term that I'm requesting a f-test and semi-partial eta square for. I'm doing this for demonstration purposes. When I put the two predictors in the model, I can then write out estimate statements that directly follow the logic up here, the 3 group means, then the 3 group mean differences. And the same is true in Stata using LinComs as well. So the model then is no longer just the same as one of the slopes. The model requires both slopes. The model is significant. So 58 for our test statistic for the model is significant. Here's my effect size. The model of dementia group differences has accounted for about 18% of the total variability in cognition. The amount of variability that remains is about 100. So a good healthy effect size. So we have the sums of squares for each of the two contrasts, as well as the contrast that I wrote to get the missing one. And I asked for these to make a point. If we look at the effect size for each of these three contrasts, so the three group mean differences that are created by the model, we have 4% for the difference between none and future, 15% for the difference between none and current, and 5% for the remaining difference. If we sum these up, it's more than the R-square. So these semi-partial eta squares that refer to particular group differences are not valid. They're not, the variables for these predictors have not been constructed in a way that the comparisons are orthogonal. There is a way to do that. It's not very useful for testing hypotheses, which is why I don't do it. So in this example and in what follows, we're not going to report or interpret semi-partial eta squares for these individual dummy-coded contrasts. Instead, what we will be asking for is the semi-partial eta square that results from the combination of these two predictors that is responsible for creating all three possible group differences. So you can't split them and look at their individual effect sizes in terms of semi-partial eta square. It doesn't work. The whole is smaller than the sum of the parts in this case. But we do have this value right here, which is what we would get if we were to combine these two slopes and ask for their joint effect size. It works out to be the model R-square in this case because that's all we have in the model. In terms of the solution, the intercept, 27, is the expected cognition score for somebody in the none group specifically because that's when these two slopes are coded, the predictors for them are coded 0. This slope gives us the mean difference of the future group relative to none, so future is lower by about 5.6, significantly so. The current group is lower than the none group by 16, again, significantly so. And if I were to take the difference in these two slopes, that gives me the difference between the future group that's part of this contrast and the current group that's part of this contrast. It looks like it would be about 11. And lo and behold, that mean difference is given to us as a linear combination of beta 2 minus beta 1. Here's my coefficient of 11. What this means is that the current group is more negative. Let me say this backwards. The difference between them, the current group is lower by 10. Let's just do it that way. That's what this means. So we have the actual means computed here for reference. So you can always tell who's higher or who's lower without having to remember your coding scheme. And I did compute effect sizes for each of the individual mean differences in terms of Cohen's d's, or in the R metric. These are okay to report. We're not talking about them as contributions to the R-square. We're just talking about them as the standardized mean difference between groups. And so the none and future groups are about 4 standard deviations apart, whereas none and current are about 0.8 standard deviations apart. Yeah, 0.4, I should say, 0.8 and 0.5. So I'm going to transition into the next video that will start looking at the results of the model in which all of the predictors are combined. So I hope to see you there.